please briefly summarize your industry education and professional background?
Right now, I'm an associate professor at the University of Missouri-Columbia in the Department of Civil and Environmental Engineering. I got my PhD back in 2007 from University of Texas at Austin, and then MS at Illinois Champaign in 2002, and then my bachelor's at UT Austin again in 2000. And so for the past 14 years, I've been a professor here at the University of Missouri. I participate in a lot of organizations, ASCE. I was a past chair of the Disproportionate Collapse Technical Committee looking at disproportionate collapse of buildings, and I'm working on the coming out with the new standards, Disproportionate Collapse Standards Committee that is hopefully coming along, and the retrofit of structures under dynamic loads. So a lot of committee work. I also do committees in ACI as well. So a lot of background in concrete and the collapse of structures.
So please describe some of the work you've already done or are working on related to reinforced concrete and its role in building infrastructure.
I started in this area back in 2007 when I got my PhD. My PhD topic was the use of CFRP to provide continuity in buildings vulnerable to collapse. And so CFRP is carbon fiber reinforced polymer, and we're looking at buildings that do not have structural integrity because they don't have continuous reinforcement. Is there ways you can use that CFRP to provide that continuity and reduce the likelihood of a large-scale collapse? Then I continued on with that work a little bit. I had a more recent project in 2011 looking at dynamic disproportionate collapse of flat plate structures. And so kind of investigating what the strength of that slab column connection is under dynamic loading rather than just the general static type loading. And then this most recent work, I've been working on the time-dependent response of reinforced concrete structures near collapse. And so instead of being dynamic, when we're looking at the other end of the scale and saying, okay, if the load's very static and it's there for a long time, is the strength as high as you would calculate with your normal calculation procedures?
Please describe the $200,000 grant you received from the National Science Foundation and what this research will entail.
So this grant is actually a collaborative grant with my collaborator, Dr. Ying Tian at University of Nevada, Las Vegas. And so I received about $220,000 and he received almost the same amount. And we're working collaborative on this topic of the time-dependent response of reinforced concrete structures near collapse. When we started to look into this topic, we're looking at what causes buildings to collapse. And we looked at previous cases of collapses, and there's several due to earthquakes and abnormal loading and things going on. But for a lot, there's no natural cause. There's no clear indication of what caused the collapse. The building's there, it's fine one day, and then the next day, it's a part of it has collapsed. And these have occurred in the US, usually on the smaller scale, usually just a portion of the building, like in a parking garage or something. But they have occurred internationally as well, such as the Sampoon department store in Korea that collapsed. It was a very catastrophic one. And so we're like, well, what actually leads from having a local damage to a large scale collapse? Is there some way we can understand that better and be able to give some warning signs or analyze that building a little bit better so we can either predict the collapse or know what to look for so it can be prevented? And so we started to look at this research, and Dr. Tian at UNLV, he's doing columns and beams to try to look at that type of behavior. And I'm looking at flat plate connections. So you have the slab and the column and what the effect of high levels of sustained load are on the strength of that connection.
Do you have any thoughts on what may have caused the Surfside collapse at this point?
I have some thoughts, and they echo what you had in your previous article. So I think everybody's thinking along the same things, but it really is going to take some time to analyze the structure and the remains of it and determine what that is. But I really hope that we can learn a lot from that collapse to make better designs and decisions for our buildings.
How do you think this research project will improve engineering techniques or infrastructure construction?
The research project is like I said, is looking at behavior structures under high levels of sustained loads. Ideally, your structure will never get to a high level of sustained load, right? You're going to be in that service level where it's nice and safe and everything's good. But if you have material degradation like corrosion or some sort of error in design or construction or overloading, you might have this high level. And so what I'm really hoping this research project can do is help us understand that behavior so that we can facilitate better interpretation of early warning signs and more prudent evacuation techniques, how we're going to stabilize that building, how you're going to repair and retrofit that building, and just overall make buildings more robust and safer, understanding that sometimes, even though we don't expect to have a high level of sustained load, sometimes that occurs. And if that should occur, how do we make that building safer?
What might other engineers learn from this particular research?
As I was going through the research, one thing I found that was really interesting is the ability of concrete to redistribute the loads. And so when we did our preliminary studies, there's lots of research in concrete, the material itself. If you put it under a sustained load, that's about greater than 80% of the concrete compressive strength, it will eventually fail within a finite time, right? And that's already in the codes. People understand that, and that's fine. What's interesting in a reinforced concrete member, once you put the reinforcement in it, then as the concrete is having that kind of creep deformation under loading, the reinforcement starts taking up more load, and this member can't actually withstand. And some of the tests I've done, 95, almost 98% of the capacity without failing within, I have a test window of 30 days. And so it's really quite a strong system once you're able to reduce that load. And that's just a single member. And an entire structure where you can distribute to other connections and stuff, it could be even better. But buildings have a limit. They try to stay standing, they want to stay standing, but eventually there's nowhere else for it to go. And then that's when you have collapse. And what I'm really hoping is this research will help us understand those signs so that we can identify cases where buildings just, they can't take it anymore, and we can prevent these larger scale collapses.
What advice would you give to other engineers seeking grants for research? How can they go about obtaining grants?
It's a lot of hard work to obtain a grant, right? First thing you have to do is to have a good idea, and so have something that is really transformative, that's interesting and new, and addresses a need. And so, my need in this project was preventing collapse of buildings. It's just an area we haven't really understood or don't understand the behavior and structure quite so well. And so we want to look into that. And then you have to research it really well. You have to figure out what everybody's done before you and come up with a good plan of how you're going to answer your main research question. And then write a really good proposal, a really clear proposal that people can understand and read. It's like, hey, you're doing this and this is how you're doing it. And, it's hopefully if that all comes together and people like it, then you can obtain funding. I've gotten a lot of grants from NSF, National Science Foundation is really great source of grants, but also the transportation industries, Department of Defense industry, they also do research grants. And so there's a lot of opportunity out there, but you have to work really hard to succeed at it.
Any tips from your experience to improve our readers' research?
The first thought I have is to have a good plan of what you're going to do. Your planning is really important, and making sure the capabilities are there for your planned work. And sometimes I think about a research project of like, oh, I can do this and this, and this sounds great. And I go and look at my lab, and it's like, wait, the strong floor is not big enough, or there's other constraints in there that's not going to work. And so you have to have a really good idea of your plan and how it's actually going to do. And then the other thing is to build a good team. All this work that I'm doing, I'm not doing it on my own. If I didn't have my great collaborator, Dr. Jan, I wouldn't be able to do this. And then my grad students are awesome. My colleagues at the university, you need that good team to be able to work on that idea together, bring in other thoughts and analysis and get the best product. And then the last thing is really be ready to make changes, because even though you have this plan, it's like, oh, I think this will be easy. I originally thought when I started this project, if I put these structures under a high level sustained load, they fail in a few days, right? Because you can't carry that amount of load for that amount of time. And they didn't. So I had to revise my research plan and be like, okay, I'm going to have a longer testing period here, and make some alterations to the research, because it's a continually evolving process. And sometimes you just have to go, okay, this is what we're learning now, and so this is where we're going to go with that.